This is lesson 60 of our no-nonsense A-level physics lessons, all about density. So just a reminder, when I say no nonsense, I'm talking about whiteboard physics. It is just me and a pen writing on the screen. That's all I'm doing, and talking at the same time. Now, why am I doing it like this? Just a reminder, I'm writing because it forces me to slow down so that you can keep up, so that you can make your own notes as we go along. I could use PowerPoint presentations, or I could use zany animations and all this sort of thing, and make the videos very short, but actually these videos should form entire lessons in themselves. So hopefully you find them helpful. So let's get cracking with density then. Density was covered at GCSE level. It's defined as the mass of a body divided by the volume of a body. And that's basically it for density. So this is going to be the mass, and this is going to be the volume, with the Greek letter rho being used for density. That is a Greek letter rho, and so I should point out that rho is not P. These are different letters, and they are written differently. You'll notice that when I write a lowercase or an uppercase p, I try to emphasize that it is a p, not a rho, by including the little tail at the top, or a right angle at the top. That's the clue. So these are different letters. This is the lowercase rho, which I suppose evolved into the Roman letter R, and this is a P, entirely different letter. Okay, so that's what density is. How do we measure density? Well, the short answer is we don't. We determine the density by measuring the mass and determining the volume. So let's just put this down. Density cannot be directly measured. It can be determined by measuring mass. That's not how you spell measuring. Measuring mass. And then I'm just going to change the color of my pen here for emphasis, with a balance and determining the volume. Now, there are different ways of determining volume depending on the nature of the body, the density of which we're trying to determine. A few important points. It is a balance, not a scale. A mass balance, a top pan balance, a digital balance, a triple beam balance, not a scale. Colloquially, they might be referred to as scales. We won't call it that. I also don't like saying we will weigh the item to determine its mass. I don't like saying that because weight is a force measured in newtons, whereas mass is measured in kilograms. It's a completely different quantity. So I don't like saying weighing something to determine its mass. A lot of people are fine with it. I'm not. I would rather say measure its mass with a balance than weigh it with a balance. I think that if we can avoid ambiguity in our communication, we absolutely should. So measuring the mass with a balance is the starting point, but then we need to also determine the volume. And that depends on the type of body. So determining volume. How do we determine the volume? Let's just do a underline because there's a little subtitle here. And there are three ways depending on the type of body. So let's start with regular bodies. If you have, let's make it like this. If we have a regular body, So regular bodies. And I should be clear, I'm talking about solid bodies here. Regular solid bodies. Then what we do is we measure the lengths associated with it. Measure the necessary lengths, and it depends on the shape. So if we were using a cylindrical body, then we would measure the diameter of the circular part and we would measure the length. And we know that the value for the volume would be calculated by doing the length of the cylinder multiplied by the cross-sectional area, and the cross-sectional area would be 1/4 multiplied by pi multiplied by the diameter squared. So it depends on the shape, so which depends on shape. And we can give some examples there. So the example I just gave was that of a cylinder, and I will do my best to quickly draw a cylinder. So let's draw that, then let's duplicate it, stick it over here on the right. This is just for example, and we're not going to go through how to calculate every volume of every regular shape. There are an awful lot of regular shapes, and it is expected that in advanced level physics you can work out how to calculate various volumes of triangular prisms and rectangular prisms, cubes, cuboids, but also things like spheres and cylinders. So we can make two measurements. We could measure the diameter, which I will call D, and we can measure the length, L. We don't measure the radius, by the way. We measure the diameter, not the radius. And so the volume would be equal to L. Let's put it the other way around. Let's do 1/4 multiplied by pi multiplied by D squared multiplied by L. Yeah, so that's a cylinder. For example, if we were using a sphere, it would be the equation for the volume of a sphere, 4/3 pi r cubed. Of course, you can't measure r, so you'd have to either calculate r or measure d and modify the equation accordingly. Remember that, I'm going to write this down because people do find this a little bit spooky. R squared is equal to half of d squared, which is equal to 1/4 of d squared. Like that. Brackets are important. To me, that seems a bit obvious, but some students actually get a bit spooked by that, and that can be quite a useful thing just to be reminded of. When they see 1/4 pi d squared for the area of a circle, they get freaked out. So that's where it comes from. Yeah, we measure the diameter of a cylinder or of a sphere using a micrometer or vernier calipers, or failing that, we could just use a ruler. But we would get a value which has more decimal places on our measurement if we use vernier calipers, or even better still, micrometers. So let's just make a little note of that. So we can measure diameter using micrometers, which are included in GCSE physics. You do need to know how to read micrometers and vernier scales in GCSE physics. You do get students saying, oh no, my teacher didn't teach that. Well, then that's a problem. Your teacher should have taught that because it is on your specifications. And then we measure the length. Depending on the length, we could use using vernier calipers I mean, we could use digital calipers as well if we aren't able to read a vernier scale, but vernier calipers, 1L or 2L, it's both the correct spelling, calipers, there's no preferred one. So using vernier calipers or a ruler, something like that. So micrometer, you'll be able to measure to the nearest 0.01 millimeters. With vernier calipers, you'll be able to measure to the nearest 0.1 millimeter. And with a ruler, you'll be able to measure to the nearest 1 millimeter. That will have an impact on the accuracy of our answer. What we'll talk about there is the resolution of the instrument, but we'll talk about resolution and accuracy and all that sort of stuff in a later video. So that's how we determine the volume. We do it, we calculate the volume, we measure various lengths, and that's how we determine the volume, which we then plug into our equation to determine the density. What about liquids and gases? In fact, let's start with liquids, because I suppose actually there are 4 things I could write here. So liquids. With liquids, what we do is we measure the volume directly. We don't have to calculate the volume. We can measure the volume using one of only 2 instruments that can actually measure volume. There are only 2 instruments that measure volume using the measuring cylinder. I don't want to call it a graduated beaker, although you might get away with that. It is called a measuring cylinder. That is the name of the instrument. Measure volume using the measuring cylinder. Done. Now, when you measure using a measuring cylinder, you do have to be careful, because with liquids, there will be a meniscus, and depending on the liquid, the meniscus might be a curving down meniscus or a curving up meniscus. It's not straightforward. So let's just draw it like this. This is my measuring cylinder, and it's got a bunch of notches here against which I'm going to measure the volume. And these are calibrated for usually water at a certain temperature. So if you're measuring the volume of something else, water at a different temperature, well, at a different temperature, the glass shouldn't expand or contract too much. We usually use a borosilicate glass, which doesn't change shape very much for temperature, but it will change a little bit. So that's going to have an impact. The choice of liquid matters as well, because some liquids you'll get a meniscus that does that. Mercury is a good example, whereas some liquids you'll get doing that, like water. So if the meniscus is concave like this, you're measuring from the bottom of the meniscus. If the meniscus is convex like this, you're measuring from the top of the meniscus. It's calibrated to take into account the extra bit of volume from these parts at the edges of the meniscus for water at a particular temperature. So there may be a systematic error associated with your measurement, depending on what the liquid is or the temperature of the liquid. But we always measure from the bottom of the meniscus anyway, and we measure at eye level. So there's a few important points there. It's got to be measured at eye level to the bottom of meniscus, and it's got to be on a flat, a level surface. You don't hold the measuring cylinder. You place it on a level surface, you bring your head down level with the meniscus, and then you look at the meniscus at eye level and read off the scale. All of that reduces what we call a parallax error. That's what that reduces. Now that text might be a bit small how I've written it there, but hopefully you can read it. And I read it out loud as I wrote it, so make it bigger and clearer if you need to. Reduces parallax error. Right, that's how we measure the volume of a liquid. But liquids are only one of the two types of fluids. And so what about gases? With gases, if we want to know the density of a gas, we can use a gas syringe. So we can measure the volume directly with the other instrument that's used for measuring volumes, which is a gas syringe. There's a few interesting points with the gas syringes. They should always be horizontally placed, so we don't have to worry about the weight of the plunger, and connected with very, very short, narrow pipes, so that the volume of those narrow pipes doesn't have to be taken into account. But then it's just, where is the plunger relative to the rest of the syringe? So if I try to do a quick sketch of a gas syringe, why am I even trying? I'll do my best. Let's do that like that, and let's do that like that. Don't worry, I'm going to delete some bits in a minute. We'll do this like this, and we'll have a smaller opening there. Right, let's get my straight line tool. So we have that like that. That comes out like this. I mean, if you're using a ruler to draw this, which you ought to be because there are lots of straight lines, then it should look quite similar to mine by the end of it. Something a bit like that, and then I can get my eraser out. I might have to zoom in a little bit to only erase the things that I want to erase. Get my eraser very narrow, or is very narrow. Oh, that's not going to work, is it? I'll leave that bit like that. Leave that bit like that. In fact, I'll leave the whole thing, because it's all going to be made out of glass anyway, so it would be transparent. So let's not faff trying to erase bits and make it perfect. So there's your gas syringe. You're going to have a scale all the way down one side like this, and you, just as we did before, you line up your eye with the scale like that. But the gas syringe should be horizontal. So syringe, this part here is the volume of the gas you're measuring. So let's just write down, must be horizontal. We do an experiment where we do put it vertically in physics, when we investigating the gas laws, but we're not going to get into that now. Okay, so the only other thing is solids that are irregular. Look, we've got liquids, we've got gases, we've got regular solids. What about irregular solid bodies? So irregular solid bodies. And there we need to use the principle of a fluid displacement, of a liquid displacement. So water is incompressible, pretty much, mostly incompressible. So water is a very good choice to use. What we do is we displace. Actually, let's write this as a sort of an instruction list. So number one, measure volume of water in measuring cylinder, and it could be a big measuring cylinder. Cylinder spelled with a C. Then, two, place body in water. Now, this doesn't work if it's a porous body, because the water will soak into the body. So if it's a porous body, you might have to spray onto the surface something that's hydrophobic to stop the water being absorbed into it. Also, it's not going to, I mean, sponges and things like that, it's not going to work. It's not going to work if the body can be compressed. So in the case of a sponge, even if you sprayed it with something that's hydrophobic to stop water soaking into it, you would still have the weight of the water above squashing the sponge down and reducing its volume because there's air trapped inside the sponge. So it's got to be a rigid body for this to work. So place the body in water, I'll say rigid body, for those sorts of reasons, and ensure it sinks so we can push it, make sure it's underwater. So we use a very narrow, very thin pin to push it down. If it floats, make sure it is immersed. It's got to be in, is it immersed or immersed? Immersion, immersion. I feel like it should be an I. Immersed. Maybe even double M. Immersed. Right, if that's spelt wrong, get in the comments and let me know. Right, question. Point number 3. So we're immersing the body in water, and then we measure the volume of the water plus the body that's in the water. And then we calculate the volume. Let's use a different color pen. Volume of body is equal to combined volume subtract volume of water. Subtract original volume of water. Now volume of water. Okay, so that is how we'd measure the volume of an irregular solid body, as long as the body is rigid and not porous. And so if it is porous, we can stop that with hydrophobic sprays, and the volume of that shouldn't be significant. And if it's not rigid, then we're going to have a problem. We might have to resort in getting a regular shaped object of the same material, measuring the density of that, and then we wouldn't care about the volume anymore because we're only using the volume measurement to determine the density. Now, what if the irregular solid body is bigger than our measuring cylinder? Well, in that case, we could do the same thing, but we displace the water. So we can use what's called a displacement can. It's just a can which has a spout on it. You fill it with water until the water just pours out the spout and wait for it to stop dripping. And that can be as big as you like. It's only got to be big enough to put the object in. Then you put that body in that water and it displaces the water and it pours out the spout. And then you just use a measuring cylinder to measure the volume of water that pours out the spout. I'm not going to write the instructions for that because it doesn't really add very much to what's already here for how to measure the volume of an irregular solid body. But it's the same principle. We're using the volume of water measured with a measuring cylinder to determine the volume of the solid body, the irregular solid body. Okay, so we move on now to alloys. So all of that is basically GCSE level. Alloys are where we add something new. So with alloys, I'm talking about two metals that get mixed together, and we perhaps want to know the density of an alloy for some reason. Or maybe we've measured the density of an alloy and we want to know what it contains, something like that. So the first thing is the alloy contains two metals. So let's put contains, let's take the simplest example, so two metals. And let's keep it general, and let's say the metals are called A and B. Metals A and B. So what can we say? We can say that the volume of the alloy, and we're just going to call that V, is equal to the volume of A plus the volume of B. That is true for alloys. Is it true for alloys? No, that's not true for alloys because they mix and it does something else. So let's just write down this. When they mix, they don't necessarily occupy the same volume. That's the whole point. So that is not necessarily true. But the mass of the alloy is going to be equal to the mass of A plus the mass of B. That is true. So let's add some notation here. This is alloy volume. I think VA and VB are obvious, and M is alloy mass. And then MB and MA and MB are, I think, obvious again. Mass of metal A, mass of metal B. Remember as well that our density is mass divided by volume. So that means that the mass of A is going to be equal to the density of A multiplied by the volume of A. And we know that the mass of B is going to be equal to the density of B multiplied by the volume B. All I've done there is rearrange the equation that we had right at the start, our GCSE equation. We also know that the mass of the alloy is going to be the density of the alloy multiplied by the volume of the alloy. And I suppose I should put down here alloy density. So I'm not using any subscripts for the alloy. Okay, fine. But the masses add together. So that means, we can say that the mass of the alloy is equal to the density of A multiplied by the volume of A plus the density of B multiplied by the volume of B. Just like that. And the density of the alloy is the mass divided by the volume. So we could say that the density of the alloy, which is equal to the mass divided by the volume, is going to be equal to rho A VA plus rho B VB, all divided by V. And you can separate that into two. So you can say it's rho A VA over A plus rho B VB over V. I think I might have said it wrong as I said it out loud, but what I've written is correct. So this is a ratio of volumes. So we can have a volumetric ratio. If we say, look, the alloy is 50% of one metal and 50% of the other, then the density of the alloy is going to be 50% of the density of A and 50% of the density of B. If the alloy is different, the alloy has, let's say, 25% of A by volume and 75% of B by volume, then we just do 75% of the density of B, 25% of the density of A, add them together, and that is the density of the alloy. So it's not too tricky to work with alloys. You just have to remember that that is true. The volume doesn't add together necessarily, but that the mass does. And then everything else just follows from the maths after that. And I'll stop there, I think. That's the end of this lesson, all about measuring density, or you can't measure them necessarily, so let's say determining densities. I hope you found that useful. We'll be moving next lesson on to springs, and I hope you'll join me then. Goodbye.